so far? Let's look. We did looking at friction of an object sitting on a flat plane. That object is still on a flat plane. However, what's different now? We're pushing at an angle. Anytime we see an angle, what do? Well, we need FPD. But anytime you see angles, what do? Sure. SOHCAHTOA. We need some trig. So, first thing we always do, though, in a force question is do what again, Reese? Draw a free body diagram. I've given you most of the forces in here. However, I'm going to redraw it right here. John, what's that downward force called? Weight. Looks great. That upward force is called what, Autumn? Force normal. Okay, we've got a downward force at an angle. And I'm going to draw it from the center to the center of the box, not on that corner there. And you'll see why in a second. That would be force applied. And then in the picture, we show friction is going to the left. How would I know friction is going to the left and not to the right? What do you think, Mal?
Because the force applied is really going to the right.
Force applied is going to the right, and friction always does what?
Resist these velocities.
Resist motion, right? So since we're pushing it to the right, friction is going to be to the left. All right. Now I'm going to draw on top of this, or I'm going to draw another one off to the side. Here's why I want you to get in the habit of doing this, okay? One of your free response questions will have you draw a free body diagram. Those are all of the forces on that free body diagram. If I start to do my trig stuff and do my components on top of this, you're now no longer having a free body diagram because you're labeling some of those forces twice. Here's what I mean by that. I have an angle here, and I need to break my force applied into its components, so I have to redraw it off to the side. And I want you to develop that skill set of redrawing your free body diagram every single time if there are components. Force applied and force of friction. Because now I'm going to come in with a different color and do my components. I'm going to break up my force applied to its downwards component and to the right. So we got force applied in the X direction, and then we also have force applied in the Y. Sorry, I got a little small in there. Let me see if I can zoom in. There we go. I really zoomed in. By redrawing it, we want to make sure I'm communicating with whoever's grading your FRQ that you understand this is the free body diagram, but this is what we need to do our equilibrium statements, to look at whatever forces are going up and down, whatever forces are going left and right. All right, what do I have here? 1,500 Newton crate is being pushed across the level 4 at constant speed. Ooh, that constant speed is important now. It's just because it's underlined and has a different color. What does that constant speed tell me? What's equal?
Your force in the X direction.
Force in the X direction are equal and in the Y. Absolutely. If your object's going at a constant speed. or not moving. Because all your forces are imbalanced. I'm not moving, right? All my forces are imbalanced. Okay. If you're going at a constant speed, same thing. I don't know where my longboard went. Somewhere around here. But I usually do the example right on my longboard, and then I hold this pose, going at a constant speed. All the forces are balanced. So what statements, my equilibrium statements, can I make from here? Whatever my force is going up, cancel out my forces going down. My force is going left, cancel my forces going right. However, we gotta do our trig, our SOHCAHTOA. Force applied in the X, and force applied, in the Y. Well, let's try that again. I got those backwards, didn't I? Man. Sorry, Radley. Force applied in the X. You guys gonna let me run up there with my mistake on the board? You might catch that and just didn't say anything. Why not raise?
Because I thought it was right.
No, my brain's just fried. Okay. Alright, let's do our trig. We've got, for a force applied in the Y direction, that is opposite over hypotenuse. So we're going to do sine. Sine 20 or 30? I can't see anymore. Sine 20. And force applied is 600. Okay. Sine 20 equals force applied in the Y direction times force, what did I say again? 600? So force applied in the Y is 600 sine 20. What mode should my calculator be in?
Degree.
Degree. So what number do we get there? Mode. Degree. Enter. $600 sine 20. 205.21. What's a real quick way to do the other direction? Instead of Y, how would we do real quick? Just do X. Change from sine to cosine. So FAX equals 600 cosine 20. $563.82. All right. Now that I've broken it into its components, I think we are ready to write our equilibrium statements. Forces are all balanced, right? Because we're only at a constant speed. So let's write our equilibrium statements. I'll do it below. Let's do it. Let's do it below. What's the first thing I need to explicitly say? Always, 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 when I write equilibrium statements. Either your object is accelerating or it's not. Since it's not, we have to explicitly say the sum of the forces in the x direction equals 0. And the sum of the forces in the y direction equals 0. Talk about some easy points on some FRQs. Like literally, this is, you get 1 point right here, sometimes 2. So it's a free body diagram. Always write out your equilibrium statements. Alright, Carter, time to pick on you. What forces I got in the X direction? I give you a hint, I got 2. I'm looking here.
Friction applied.
Friction and force applied, right?
Yeah.
So those cancel each other out, right? Because one's going left, one's going right, they cancel each other out. How many forces I got going up and down there, Mr. Powers? Got 2? I count 3. We got 3 vertical forces, right? What forces are going up?
Force going up for force normal and
That's it. Don't say anything else on your mouth. Right? What forces are going down?
F, A, Y,
Yeah,
and then late.
absolutely. We're looking for the coefficient of friction. I'm missing something here. There's something, there's one of our functions or one of our formulas we can expand upon to get the coefficient of friction. Well, that's going to be the friction one, right? What's the formula for friction again that we wrote down in our notes? Friction equals mu force normal. Well, I got this picture pulled up. What's the difference between static and kinetic again?
Static is staying still, and then kinetic is.
Absolutely. My question for you, is my object moving here?
Yes.
Yes. So this is technically kinetic friction, which is why we're finding the coefficient of kinetic friction between the floor and the crate. So we can actually expand this out to be mu force normal equals force applied in the x direction. Right? Which expanded a little bit. I think we got all of our pieces in order. I think it's just plugging and chugging from here. Force normal. I don't know it, but do I know force applied in the y direction? Do I have a number for that? What's that number, Troop? 205. Do I have weight?
I don't remember.
It's the second number, it's the second word in the question, right? A 1500 Newton crate. All right, it tells you the weight. Hey, so force normal is 1705. Where can I use that number at now? Can I plug that in over there and find mu now? Absolutely. So mu for kinetic friction equals, what do we get for x direction again? 563.8, so I'll just do 563. Am I reading that right? Oh, yeah, 563, I'll do 564. I'll round it to whole number. We finally get our number. 564 divided by 1705. I get 0.33. Troop, what's coefficient of friction's unit? There isn't one. I thought you were saying I don't know. There is none, right? Well, why is there none? Because we just divided newtons divided by newtons. Hey, those cancel out. So there is no coefficient. Feeling okay? That's a big one. That's a big problem. Okay. We have the same situation, same crate, same force, but instead of pushing into the box, we're now pulling. All right? This does change your system. This now will hopefully let you quantitatively see, and hopefully maybe you've experienced this, why is it easier to pull something than it is to push it? There's a physics reason behind that. Because when you push something, you have to push it across something and into the ground. So basically you're essentially making friction more. When you're pulling something, you're not only pulling it backwards, but you're also lifting it off the ground, which means force normal gets smaller, which means there's less friction, which means it's easier to pull. So that's why if you ever have a dolly with like a fridge on it, why you should always pull the dolly, because it's easier to pull the dolly than it is to try to push it. Okay. So I'm going to let you hear. I'm going to give you a couple minutes. Try it out. Do your free body diagram. Judo chop on it. Break it up. Get your components. Your weight of the box is the same, and your coefficient of friction is the same. Your force normal is not. You can keep working. I'm just going to start off and write some stuff. Okay, I made a mistake. I intentionally made a mistake.
It's not zero because it's accelerating.
Absolutely. Now, which one's not zero?
It would be in the X direction, right?
Absolutely. Okay. The box is going to accelerate now. We're not lifting it off the floor. We're accelerating across the ground. So that means my forces in the Y direction are balanced, but not my forces in the X direction. So that one is going to be MA. So MA equals, what are my forces in the X direction? Which one is going to be bigger? And that's the direction you're going in, right? Friction will never be bigger than, well, it could be actually. So the box is now going to the right. So my X force to the right is bigger than FAX minus force of friction. Forces in the Y direction, though, what do we got? We've got weight going downward, so it's weight equals force normal plus FAY. Now, the mass of the box isn't given, but we can find it, though, right? If weight is 1,500, how do you find mass?
Gravity.
Divided by gravity, right? So weight is mg. So mass would just be 1,500 divided by 10, right? So my mass is 150. I don't know acceleration. Force applied in the X direction. That would be 600 cosine 20 minus mu force normal. I'm running out of space here. I'm gonna rearrange this just a tad. What's that number we got from mu earlier? 600 cosine 20. What's that? I need a calculator. Where'd my calculator go? 600 cosine 20. We got 563 point. I'll just do 564. It's just rounded number. 0.33 force normal. Hey, that was 1,500. Don't know what force normal is, but force applied in the Y direction, what is that going to be? Do you have that number, Luke? Force applied in the Y direction?
205.
Absolutely. Can we just round it to 205? You okay with that? Okay. Mr. Williams, you seem to be rounding a whole lot of numbers. Well, sure. In the grand scheme of things, if I gave you $205, would you sweat 21 cents? No, right? So in the grand scheme of things, rounding has got a very small window of error. So 1,500 minus 205, force normal, 1295. 150, acceleration, what's that, times 0.33. So I get 564 minus 427. Acceleration comes out to be 564 minus 427 divided by 150. Acceleration is 0.91 meters per second squared. Going okay? Just doing pulse check. Brake check. Slow down a little bit. Here's what I want to do. I want to give you time in class now to work on those homework problems that deal with specifically objects being pushed or pulled at an angle. What I'm not talking about is objects that are sliding up and down a ramp. Okay? We'll save that for tomorrow. All right.